One can be a register or memory, the other has to be a register. The ones we have studied in computer architecture and organization courses, we'll stick to that. Some of the instructions are of very basic nature, so there is nothing very unusual about these instructions. These are plain vanilla like move, add, sub, jump, these kind of instructions. The interesting thing here is this is the convention I follow, and in exam also I hope everybody will be following that. Otherwise, you will be mentioned explicitly. Is that the first operand
Sir, here R0 is a register.
yes, R0 is a register. Yeah, that's right.
So, sir, here 3 address is strict, or I can give 4.
No, I'll talk about that. Okay, you cannot give 4, but you can definitely give less than 3. Okay, so that is possible. Yeah. Now you can see that the source is the first operand always, and the destination is the second operand. So when you issue the instruction move y comma r0, that means value from the memory location y will be transferred to r0 register. Similarly, when you say add z comma r0, that means the content of memory location z will be added to the content of the r0 register. And when you say move r0 comma x, that is basically the store instruction, which is storing from the register to memory location. Okay, you know all those variables you declare in your C program is nothing but translates to some memory location. But you know that sometimes the architecture does not permit 2 operands fetched from memory at the same time. That is not permitted. Sometimes the architecture requires you to use the load store architecture. That means everything should be loaded into registers, and then only operations can be performed, ALU and other operations. Also, it requires less memory to use register-based addressing. So all these facilities are there, plus the basic facility of using register much faster than accessing memory location is of course there. So there are 4 reasons why you always try to avoid memory location based instruction scheduling and try to use as much registers as possible. So most probably Y, Z, and X, they all be in register locations before any of the operations are executed. But the problem is, since you can have infinite number of variables in your program, so infinite number of memory location requirement, in order to accommodate them in a limited set of registers, maybe 32, 64, 128 at most, you have to use registers efficiently. Now, you see that because of mechanical instruction selection process, this kind of instructions, as you can see later on, A is assigned the value B plus C, and D is assigned the value A plus E. See what kind of translation it happens. So A is assigned the value B plus C, as you can see right here. It is move B comma R0, add C comma R0, move R0 comma A. So this is the A is assigned the value B plus C part. And then we have D is assigned the value A plus E. You see that here we are issuing the instruction move A comma R0, add E comma R0, and move R0 comma D. So you can see that the 4th statement is a redundant statement because you have already computed the value of A in register R0. And then you are fetching A from memory location to R0. But A is actually in the R0 register anyway. So you don't need the 4th instruction, move A comma R0, which is explicitly moving the memory content A to R0. It's not needed because R0 already contains the updated value of A. And if you don't need A after this piece of code, you actually can eliminate the third instruction as well. That means you don't really need to store R0 into A if there is no immediate use of this value. Okay. So this is something called live variable analysis. It's beyond the scope of this course, but I'll just touch briefly why it is so important.
Sir, is this topic important for GATE?
Very much. Very much.
Oh.
Okay. So instruction selection, if the target architecture contains an INC instruction, then A is assigned the value A plus 1 can be implemented as INC A, and you know it will require very less memory cycle. But if you want to do the more costly sequence, which is the more mechanical sequence, then you bring in A into R0, the register, add the immediate value 1 to R0, and then move R0 to A. And you can see there are 3 instructions, plus adding an immediate value requires a lot more cycles. So definitely instead of INC A, if you use these 3 uh, set of instructions for performing the same thing, it will be more costly. So intelligent instruction sequencing and selection is important. As I said, our instructions will be of the form op, source and destination. Op can be move, add, sub for the timing. Now, what does a simple code generator do? As you can see, it does only 3 specific tasks for the timing. Actually, it can do a lot more thing, but for the timing, we'll assume it just only the 3 basic things it is supposed to do. Okay, and these 3 things, as you can see, is use the register, or I would say maintain the register and address descriptors. I'll come to these entities in detail. Then use the code generation algorithm, which is a standard algorithm, to perform the actual code generation. And as you'll see, the code generation algorithm requires usage of a function known as getReg, which assigns registers, you can say. We'll talk about that. Okay. So this is where we are right now. Um, Now, what is a register descriptor? Please read it. As you can see, register descriptor keeps track of what is currently in each register. Okay. So it is kind of a table you can think of, which has registers and what are the things in it. Means what are the variables it is storing at that time, at this moment. Now you can wonder why it is needed, because generally a particular register can hold only a single variable value at a given time, but we will see using our algorithm it can occasionally, in fact very frequently, it can contain more than one values. We'll see why and how. Now this particular entity is consulted whenever a new register is needed. So whenever you need a new register, you have to consult this. If a particular register is free, there is no problem, but chances are that you have thousands of memory variables and you have, I don't know, maybe 32 registers. So if you want to map all the memory variables into a register, it is impossible. So what you can do is you can use the spilling process to force a particular register to become empty by storing the value it contains into memory locations. Like for example, suppose A is in R0 and you need R0 for B, so you have to spill R0 to the memory location of A, and then R0 is forced into emptiness, you can say, and that can be assigned to B. Okay, so that is why this is not the only reason, but we will see there are many reasons why why the register descriptor needs to be consulted whenever a new register is needed. And as you will see, as the code generation process progresses, each register will hold the value of 0 or more names at any given point of time. Just the counterpart of register descriptor is the address descriptor. Please read it. I'll explain it. An address descriptor keeps track of the locations where the current value of the name can be found at runtime. So it is just the other end. Every register keeps track of the variables it contains currently. An entry in the address descriptor is basically referenced by the memory variables, and now this memory variable in this descriptor table tells you what are the registers where the current value of this particular memory variable can be found. Suppose A is in R0 and R1. That means the address descriptor should contain an entry for A, and the corresponding values should be R0 and R1. Now, obviously, the register descriptor for R0 will point to A, and register descriptor for R1 will point to A as well. Okay. So this is how they are interrelated. But as we will see, things are not so simple. That's why we need two tables. Just one table is not sufficient. Also, the address descriptor doesn't have to be a register all the time. It could be a stack location, it could be a memory address, etc. And when a value is copied, the value stays where it was. Okay, that means the source is not destroyed. So now the same variable can be found in two locations, whatever they are. Now we'll come to the code generation algorithm. Please take a look at it before I start explaining, because most of the things are self-explanatory.
Then who is the descriptor here?
Descriptor is nothing but a table. You can think of it as a table. Okay.
No, the address table, I can say that. The address table for y to determine y prime.
Yes. Yes. But we'll use the formal name, which is that descriptor. Okay. We'll see
Okay.
examples. Don't worry. We'll come to that in 10-15 minutes. Okay. The CG algorithm is pretty big, uh, but it's mostly self-explanatory. It's not that it is very complicated. It's mostly intuitive. So if you have a statement of the form x is assigned the value y plus z from your intermediate code generation step, then what should you do for the code generation step? The first rule says that, as I said, most of the operations should be carried out in register if possible. So first step is rule number 1 is invoke getReg to determine the location L where the result of the computation y of z should be stored. So that is the first step. In general, L is a register, but it could be a memory location as well. We'll see why. Okay. So note that L is generally a register. The second clause will come only less frequently. So this is the first step. So that means you determine first what is the register where the result would be stored. Am I clear? Okay. Second rule says, now what you should do is move the first operand, in this case that is the y, into L, and then your statement should be operate z on L. So if it is plus, it will be add. If it is minus, it will be sub, and other forms of operation. For binary operations, I'm talking about. Binary operations, it could be arithmetic, it could be logical, doesn't really matter. Okay. So first thing, you generate the register. Second thing is you move y into that register. Now, how can you move y into the register? There is an interesting thing here. First, you consult the address descriptor for y. So address descriptor will tell you where all the locations y is currently available. Now, it could be that y is in a register. So instead of moving from y to a register, you can simply reuse the register. That's it, as simple as that. So that means when you consult the address descriptor for y to determine y prime, that means all the current locations of y, prefer the register for y prime. That means y is in a register and y is in memory location, so prefer the register. If y is not already in L, L is computed as you can see in rule 1, that means it's probably a register, L is probably a register. If y is not already in that register, generate the instruction move y prime comma L to place a copy of y in L.
Sir, in this line, I had a confusion. Sir, it is telling that if y is not in register L, so generate instruction y prime comma L. Sir, why y prime?
No, it is basically y, but y could be in some other location as well. Okay, that is what I'm saying. So in that case, that should be started. In general, yes, if y is in only in memory, you should not use this. Okay, all right. But who knows? Y might be in somewhere else where it is faster to use. Okay, in that case, you should use it. And definitely, if y is not in any register, you have to bring the copy of y into a register. Okay, so that's what it means. Am I clear?
But sir, y prime is the replacement of y, I can say.
No, y prime is not a replacement. I'm saying is suppose y, suppose, okay, let me show you this thing. Just a second. I'll share it.
Sir, if we show it with the example, it will be clear.
Yeah, I'll do that. Okay, let me share my entire screen. I'll be bringing the, yeah, like here. For example, suppose you have already done this in some other step. So move y comma r0, sorry, suppose the statement is like this: y is assigned the value x plus z. Okay. So what is the 3 address code you have already generated? Move x comma r0, add z comma r0, move r0 comma y. Okay. So how does the address descriptor table look like? So this is the address descriptor table. It has a few entries. So entry for y, what should be in there? Entry for y. So y is both on y and in R0. Okay. Now the next statement you have encountered is this guy. After some time. After
Sir,
some
in the third step, after adding z into the register, actually register containing the value of y, so you are doing r not in y, means x plus z will be in y.
x plus z will be in y and x plus z will be in R0 as well.
Okay,
Right?
sir.
Right? So now if
Yes,
you
sir.
do this statement, y plus v, then what? Your get range will consult this guy right here. Okay. And it will say y is available in y and y is available in R0 as well. And this is basically y prime. So y prime is nothing but y as well as R0. Okay. Am I clear?
Yes, sir. Sir, but when you do the instruction move r naught comma y, sir, at that time from the register r naught is value will be moved to y.
No. As I said, this is the statement I made. Na? Please look at this. When copied, a value also stays where it was. I have already said that. Clear? Okay. Am I
Sir,
clear?
but here we are doing move, not copying, sir.
No. Move means what? Move means copy only. Okay.
Okay, sir.
It's not a uh, cut and paste. Okay. It's a
Okay,
copy
sir.
and paste. Okay.
Okay, sir.
All right. So that's why we are not using y. Instead of that, we are using y prime. This is something, yes, Pranay is correct. This is something a little confusing at first, but as you go forward, we will see. And you will see that y not only stays in y and R0, it could be some other memory locations as well. So that is more dangerous, but probably not all situations will be available today. Okay. So, but situations like that can come. That's the point. Okay. Okay. Now, the rule number 3 says generate the instruction of z prime comma l. Again, same concept. Instead of z, we are not using z, we are using z prime. Z prime could be a register. So again, prefer a register to memory location if z is in both. Okay, now the point is, now since you have already done this, see what you have done here. What you have done here is you have moved x to R0, you have added z to R0. So that means R0 now contains z plus x, which is nothing but y here, right here. Okay. So that's why I'm saying you have to update the address descriptor. Here we are using x. In our example, we are using y. So let's do that. So let us go to our old one, which is x plus y plus z. So move y comma r0, add z comma r0, and move r0 comma x. So now in the register descriptor table, this is the register descriptor. Sorry. In the register descriptor table, which is the red one, you will have entry for R0, what should R0 say? R0 will say it contains X. So as you can see, after this move R0 comma X, you have X in R0 and R0 pointing to X. So both the address descriptor and register descriptor tables are updated. This is what is meant here. So update descriptor of X to indicate X is in location L, that means X is in R0. If L is a register, update the register descriptor to indicate that it contains the value of X. Okay. So R0 is now pointing to X. Now, suppose R1 also had X. Now, suppose this was the situation. R1 containing X. This was the previous situation. So what will happen now? Of course, the updated value of X is now in R0. So we have to remove this entry. And we have to remove all such entries. That means for remove X from all other register descriptors apart from R0. What is rule number 4? This is slightly difficult to understand. If the current value of Y and or Z have no next uses, means they are not used anymore, are not live on exit from the block. That means they have already been used. They are not live. And they are in registers. Then what should you do? You should update the register descriptor to indicate that those registers no longer will contain Y and or Z respectively. Okay. That means suppose this was the case that R1 contain Y, and you no longer, after this block is executed, this is the block, and after that Y is not used. You don't use Y anymore. Then what? You can say that R1 does not contain Y anymore. Same for Z. But if Y is further used, you have to keep using it. So if it is still used, you should not do this. But if it is never used, then you should remove those values from the register descriptors. Why? Because then the precious resource registers will be available for accommodating other variables instead of using some stale variables. That's what we do, right? I mean, if we don't need something, we basically throw it away. We don't store it anymore. So why should you store somebody who is no longer needed? Now, this is the special instruction. So this is the basically copy instruction, not a move instruction. Okay. So now after this instruction, the value of Y will be in Y and it will be in X as well. So that's why I was telling you that this Y prime can be in multiple locations. It need not necessarily be in its own memory location and a register. It could be in multiple locations as well. Like for example, after this instruction, X also contains Y.
If sir, Y prime is a replica of Y.
Right, correct. Which holds the currentmost values of Y. Okay, currentmost value of Y. It could be multiple locations. It could be registered, it could be a set of registers, it could be a set of memory locations, as I said.
Sir, as the address of Y and Y prime can be same.
It could be same as well. For example, it is not in any register, it is not in any other memory location, then it will be same. Okay. So if Y is in a register, simply change the register and address descriptor to record that the value of X is now found only in the register holding the value of Y. That means what? That means suppose suppose R1 contains Y, R1 contains Y, and R2 contains Y as well. As I said, it can be contained in multiple registers. Now, after the instruction X is assigned the value Y, you should say that R1 contains X as well and R2 contains X as well. This is what this thing means. So if Y is in a register, simply change the register and address descriptors to record that the value of X is now found only in the register holding the value of Y. But if Y is in memory, we use getReg to find a register to load Y and make the register the location of X. So if currently, so I am assuming Y is in R1 and R2, but it could be that Y is in neither. Y is in its own memory location only. Okay, then what should you do? The first thing you should do is issue this instruction. Say move Y comma, say R1, say R0 is not available. You assign the move statement Y to give Y to R1, and then you say nothing. I mean, you say that now X and Y contains are contained in the same location. So you can say R1 contains Y and R1 contains X as well. But you have to generate this instruction move Y comma R1.
Sir, when R1 is containing Y, so we can add X into R1, I think.
Absolutely. You are not adding, you are just mentioning that in the register descriptor, that R1 contains both Y and X. This is where things are so interesting. Okay.
Sir, but when R1 containing both Y and X, so in which form it will be contained? In multiplication, addition?
Everywhere. It will be contained as it is. Means R1 contains both Y and X. That's it. Now, if you generate an instruction like this, suppose you are having this instruction. After this, you are doing, say, Z equal to X plus, say, W. In that case, you should not generate this. Move X comma something or hash or something like that. You cannot do that because X is already there in R0. So you, R1. So you can just say move, op you can just say op, since X is already contained in R1, you can say R1 op, since we are using source first, so op W comma R1, or rather we'll use add W comma R1. That's it. That means we have added W to X. Am I clear? You don't need to do a specific move X comma some register instruction because a register R1 already contains X, which is available from the register descriptor corresponding to R1. So this is the special case, and there is a rule 5 as well. Once we have processed all 3 address statements in the basic block, we store by move instructions those names that are live on exit and not in their memory locations. So how can you be sure about variables which are not in their memory locations? You just look into the register descriptor, because if the register descriptor contains some names and the address descriptor does not contain that, that means what? That means that suppose you say that R1 contains Y and X, okay, but you see that there is no entry for X here. So X is R1, this is not there. That means what? The current value of X is not updated in the memory location X. So this entry is not there, suppose this entry is not there. So what does it mean? That the register contains a more updated value of X, and that updated value is not yet stored in the memory location X. So you need to do what? You need to move this X from R1 to X itself. So you need to generate that statement. That's what it means. So that means if the variable is live on exit, how do you calculate live on exit? I'll come. But if it is not in their memory locations, then you use the register descriptor to determine what names are left in registers and the address descriptor to determine that the same name is not already in its memory location. In that case, what you do is use a move instruction to store those names. Now, how do you find out whether a variable is live on exit? We are not going to probably go into the details, but you can see that the live variable information is available. Live variable information, live variable analysis is a very interesting topic. Unfortunately, I don't think we'll be covering it in detail here. Let's see. And that's where the concept of basic building blocks and things like that come into picture. Now, as you can see, the code generation algorithm relies heavily on the getReg function. So what does getReg do? Let's see. GetReg does nothing, but it returns the location L to hold the value of X for the assignment. X is assigned the value Y of Z. So first step is, if the name Y is in a register that holds the value of no other names, Y is not live and has no next use, then return the register Y for L. That means Y is no longer needed. So you can use the same register for X. That's what it means. Now, if this register holds other values like X, Z, etc., you cannot do that easily, because then you have to be careful, because those values will be lost also because of side effect of this instruction execution. So you cannot do that. You have to be careful. You can do that, but then you have to take precautions. Update the address descriptor of Y to indicate that Y is no longer in L. That means you cannot find Y in L anymore. Step 2. Failing step 2, return an empty register for L if there is one. That means if Y is not available in a register, of course, you have to find an empty register and then issue the move Y, L explicitly, as I have already mentioned in the first step of code generation algorithm.
Sir, Y can be present in hard disk?
Yeah, no, Y cannot be present in hard disk, because we are talking about a program in execution. Okay, so if a program is being executed, it has to be in memory. It cannot be accessing something from the hard disk. Okay. Okay. Now, step 3 is interesting. Failing step 2, that means we could not find a suitable register for storing X. Then what will happen? Then that means there are some variables in registers which need to be spilled. Okay. You have to force them to empty. Now, the problem is, how do you find such a candidate? Which register to be emptied? So, in that case, what you can do is find an occupied register R, store the value of R into the corresponding memory location by consulting the address descriptor, consulting the register descriptor, update the address descriptor for that particular memory variable. So, for example, suppose you are choosing R0 and R0 now contains W. So, you have to update W, entry for W, to note that it is no longer in R0. And then, of course, you make the store instruction move R0, W. That's what you have to do. Then return R. If R holds more than one variable, like it could be W, then V, then S, all those variables are in R0. Then since after this instruction, R0 will contain only X, then all those values need to be copied to their memory location using move instruction. So there will be several move instructions. So that means the getReg register should use a heuristic which says that it should not spill a register that contains too many memory variables. Okay, so some heuristic has to be used. So you can see A suitable occupied register might be one whose datum is referenced farthest in the future. That means if it is spilled now, there is not much harm, because anyway, it is not needed right now. And one whose value is also in memory. That means it is already in memory, something like that. Okay. So you get a copy of it. You don't really need a move instruction for those variables because the values are already updated in memory. These are basically interesting exercises. Unfortunately, we don't have time to do that this year. I have done that in earlier years, and you can easily come up with interesting new heuristic and prove that it is actually working. And if you simulate, you can show that yes, your algorithm is doing better. So these are interesting research topics as well. Register allocation and assignment are very, very much still people are doing lots of research in that, and there are lots of interesting techniques. Last couple of years I have given interesting problems for them to solve.
Sir, is this
Like
heuristic in
using
nature?
puzzle solving. It is very much. So two techniques which people commonly used earlier is, one is graph coloring problem and another is the puzzle solving problem. Unfortunately, I don't have the time to go into the details, but these are interesting research topics, and last couple of years a lot of people did those things as part of their theoretical assignments in my class. Now the last step is, which is the worst case, if X is not used in the block, that means you don't need X after this instruction anymore, and also no suitable occupied register can be found. They are all used heavily. So how can you spill them? In that case, the memory location of X can be used as well. Okay. And there are some exercises. I don't want to go into the detail. Now let us look into an example. T is assigned the value A minus B, U is assigned the value A minus C, and V is assigned the value T plus U, D is assigned the value V plus U, and D is live on exit. So you have to store D. You have to keep storing D. You cannot discard it. So for instruction A minus B, A minus C, T plus U, which is nothing but A minus B plus A minus C, and D is basically addition of that. So first instruction is T equal to A minus B. So you can see the generated code. We assume that there is no the address descriptors and the register descriptors are clean, so no entry before that. So you can see what it does is, first it gets the register R0 and make a statement move A comma R0. Okay. So this is the, and I have shown you the corresponding step number in getReg and the rule number in CG rule number columns. You can match them. I'm not going into the details right now because it will take too much time, but you just take my word for it, and later on you can check whether it is correct or not. So move A comma R0 is generated, and then sub B comma R0. Okay. So after this instruction, what happens is, as you can see, the register descriptor says R0 contains T, and the address descriptor says T is in R0. Nothing else can be said because A and B are not in any register anymore. After the second statement, U is assigned the value A minus C. Now you need to find the next register if it is available. Since R1 is available, you can move A to R1 and sub C from R1. So now R1 has U and U is in R1. And of course, R0 has T and T in R0. These are carried over from the earlier step. Now, when you do V equal to T plus U, now what happens? You can see that T is now in R0. So you don't need to issue an instruction move T comma R0 or something like that. You can fetch the value from R0, and then that would be the target for V, and then you add U into that, and U is also available in a register which is R1, so you don't need to move from U to a register, it is already there. So you just use only a single instruction, add R1 comma R0. So as more and more such arithmetic instructions are there in your intermediate code, you can see reuse of register increases heavily. That means you basically get smaller and smaller set of machine instructions. That improves the efficiency of the target code. And you can see that after this instruction, R0 no longer contains T. R0 does not contain T anymore, but R0 contains V. And V is in R0, and as you can see, R1 continues to hold U, and U is in R1. Now, the next statement is D is assigned the value V plus U. Now, V and U both are available in registers. So, V is in R0. So, you use that as the target and add U onto that. So, add R1, comma R0. So, now R1 contains, okay, now that's what it is now. So, R0 is now containing D. And as I said, D is live on exit. So, you have to explicitly issue the move R0, comma D instruction to store the value of most updated value of D into its memory location. And you can see that we are no longer storing the register descriptors for U because it is no longer needed. So R1, the entry for R1 and the entry for U are deleted from register descriptors and address descriptors respectively. But we include the new entry that R0 has D and D is R0 and in memory as well. So this is where our block of intermediate code here is successfully converted into machine code, which is the second column, as you can see. If it is a conditional instruction, we can use this kind of instruction comp x comma y. So if x comma y go to z, we can issue comp x comma y and then cz smaller than symbol z. That kind of instructions are possible. Now you can get this kind of examples in your exam, exercises in your exam, and I have given one in yesterday's assignment, theoretical assignment. So you can assume the number of registers and then try to generate the code. Of course, first you have to convert this code into intermediate code, and then only you should be going into the machine code. As you can see, this while statement is not available for intermediate code. So you have to get the corresponding intermediate code first, which will be some kind of if code followed by a goto code. Okay.
Sir, when our theory exam will be happening in February?
Have you got any notice from the dean, HOD, or any of the persons from controller?
No, sir, still not.
Okay. I have got some information, so I cannot really disclose now. I am hoping it should be after the GATE exam is over. Okay, now that GATE exam is fixed, the days are fixed. I think after your GATE exam is over, and with some gap, you will get your exam started. Okay, I think so.
So actually, it is very bad of GATE, sir, to conducting the exam in such a COVID situation, sir.
I cannot comment. You can see the social media full of lots of things, so cannot say anything. Okay, I'm just skipping these, the algebraic identities. Array references, we are not touching this year at all. Now, interesting point is register allocation. So when you are doing a register allocation, you have to follow the memory hierarchy, like file system, main memory, L3 cache, L2, L1, and then register. So capacity reduces and access time reduces as well as you go from one level of the hierarchy to another. Critical to allocate and assign registers for efficiency. As you can see, there is a 10x performance difference. I think you all know why it is. Also, C allows register variables. Some of you might have done that. Register allocation could be mapped into the graph coloring problem, which you are not going to touch. So you can skip this. Now we'll go to the next topic, which is the concept of basic blocks and control flow graph. Pranay is excited about it for a few days, like leaders and things like that. So you'll see what they all talk about. A basic block is a maximal sequence of consecutive 300 instructions such that it has a single entry and a single exit. So control flow enters the basic block through only the first instruction in the block, and controls leaves the block only after the last instruction. So between this first and last instruction is your basic block. How we define a first instruction and last instruction will be cleared very soon. If control reaches a basic block, all instructions in it are executed in sequence. That means one after another. In the sequence, they appear in the basic block. No branching or jumps are allowed in between. So you cannot jump off in between. You cannot jump off in the middle or make a jump from another place into that. You have to enter using a sequence. And basic blocks together form a control flow graph. Okay. Now, some of the benefits of using context-free graphs is you can easily understand the code generation algorithm, and it can be used for finding inner loops. So you might have seen some programs which check the code coverage and analysis and stuff like that in your software tools. So they basically might be interested in this kind of a graph. Okay, we define, okay, we explain these terms which you are already using so many times. What do we mean by define? What do we mean by use? And what do we mean by live variables? So if you look at the 3-address code, X is assigned the value Y of Z. Then this TSC defines X. TSC means 3-address code. And it uses or refers Y and Z. So this is how you say where is a variable defined and where is a variable used. So use and definition, these are important terms for a variable. And here you see the definition of these things. Now, what is meant by a variable live? A name in a basic block is said to be live at a given point if its value is used after that point in the program. Okay, that is very important. Need not be in the same block, could be in a different block. So that means you are defining X, and then at some later point, you are using X. Okay, and this is basically known as the next use of X. So if I is defining X, statement number I is defining X, and statement number J is using it, then statement J uses, the next use of X after I, statement number I is statement number J. So we say next use of X is J after I. This is also an important term. So define, use, live, and next use. These are the 4 terms. Now comes the important thing, which is very much needed for your exam, is how do you partition into basic blocks given your sequence of 3-address statements. We'll see an example. In fact, we'll start with the example and see how it looks like. This is an example. The left-hand side is the high-level program. The right-hand side is the corresponding 3-address code, sequence of 3-address code. Okay. Now you can see that in these statement numbered 1 through 12, there is no branching in between, or there is no jump in between. It starts from statement number 1 and it continues the execution at statement number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And at statement number 12, there is a conditional go to. Okay. So that means if you enter via statement number 1, you have to exit via statement number 12. So this is a basic block. Okay. So as you can see here, in this particular code, it is not so. So we have I. Okay, don't look at the right hand side right now. Okay, just look at the left hand side. Let me see. Yeah, I think I can do this. So what is happening here is I equal to 0. Then there is a label L2 where j is assigned the value 0. Then there is a label L1 which is T1 equal to 10 star I, T2 equal to T1 plus j, T3 equal to 4 star T2, T4 equal to T3 minus 44, AT4 equal to 1, j is assigned the value j plus 1. If j is smaller than 10, go to L1. So you can see in this block, there is a jump in the middle. It is a conditional go to, which goes to L1. So L1 can be reached after j equal to 0, and it can be reached from this statement as well. If j is smaller than 10, go to L1. So this is not a basic block. Then you have I equal to I plus 1. Then if I smaller than 10, go to L2. This is another conditional jump in between, which goes to L2. So L2 can come from two places. One is after I equal to 0, and another from the conditional jump inside this block. Not a basic block, but some block. Then you have I equal to 1, then you have L3, then you have some statements, and then if I smaller than 10, go to L3. So L3 can be also entered via I equal to 1, and then after, if I smaller than 10, go to statement. So this is not a basic building block. So you have to partition it into basic building blocks. And what are the rules?
স্যার বোধহয় ইফের আগে অবধি এ ব্রাঞ্চ করতে হয় না ইফ
Correct. Let us see the rules. Okay, let us see the rules. So the first rule says that you have to calculate something called leaders. Okay, so this is how you partition into basic blocks. So there are 3 rules in step 1, and we'll come to step 2. So what is step 1? So what is the algorithm doing? Partition into basic blocks. Input is a sequence of 3 address code. Output is a list of basic blocks with each TSC in exactly 1 block. Okay, so all TSCs are now partitioned into different basic blocks. So how do you do it? First is we determine the set of leaders, the first statement of basic blocks. So what is the definition of a leader? The first statement of a basic block. Very important. So each basic block starts with a leader. A leader can be only present in one basic block. So what is the first rule? The first rule is the statement number 1 is a leader. So if you are given a sequence of 3 address code, like here, statement number 1 is a leader. Here also you can see I is assigned the value 0 is the first statement on the left hand side, so that is a leader.
So for loop is also a conditional statement, I think.
Yes. In intermediate code, there is no for loop. It is always translated into if then else followed by a go to. Okay.
Yes, sir.
Rule 2, any statement that is the target of a conditional or unconditional go to is a leader. Okay. So let's see how many leaders are here in the left hand side. You can see L1 is a leader because it is the target of the statement if I smaller than 10, go to L1. Similarly, L2 is a leader, which is j equal to 0, because if I smaller than 10, go to L2, this statement makes a jump to L2. Similarly, L3 is a leader, because I smaller than 10, go to L3. This is the target. This makes L3 as the target. So we compute the leaders here. The first statement I equal to 0, then L2, which is j equal to 0, then L1, which is T1 equal to 10 star I, and then L3, which is T5 equal to I minus 1. These are all leader statements. Okay. So So rule 2 gives you the different leaders. And also rule 3, any statement that immediately follows a go to or a conditional go to is a leader. So not only the conditional statement creates a leader with its target branch, the next statement is also created as a leader. Okay. So for example, in this example, you can see 3 is a leader because statement number 12
So number of, say after building a block, number of edges can be asked.
sorry about that. Okay. Yeah. So you can see that statement number 3 is a leader because it is the target of statement number 12. So 1 and 2, so 1 is a leader, 3 is a leader, and because 12 is a conditional go to statement, anything after 12 is also a leader. Okay. Now, what is the step 2? This is how you partition the block of 3 address code into basic blocks. For each leader, its basic block consists of the leader and all statements up to, but not including the next leader or the end of the program. So that means the leader and all following statements till the next leader is a basic building block. The next leader should not be included. So here you can see 1 is a leader, 3 is a leader. So in between all statements should be in the first basic block, which is 1 and 2 basically. From 3 onward, it is a separate building block. After 12, we'll start another basic building block. With this rule, we can compute the left-hand side intermediate representation into the right-hand side basic building blocks. So as I said, I equal to 0 is first building block B1, as you can see.
So his first statement is always a leader.
As you can see right here, B1, sorry, I0 is in a basic building block, which is B1, because its following statement, j equal to 0, L2, is another leader. Now, immediately after j equal to 0, L1, starting from L1, is another leader. So the second building block consists only of the statement j equal to 0, as you can see. So B1 and B2 are well defined. Now, from third statement onward, up to the conditional statement, if j smaller than 10, they all belong to the same building block, because the statement after a conditional go to is a separate is in a separate building block, because it is another leader. So you can see from T1 equal to 10 star I to if j smaller than 10 go to B3. Okay, we are going to not going to use L1, but as you can see, L1 is basically the starting point of B3. So either you can use B3 or you can keep the label L1 as it is in front of T1 equal to 10 star j, and you can say if j smaller than 10 go to L1. That is also possible. You can keep that. Now immediately after that you have the I equal to I plus 1 statement, and then if I smaller than 10 go to L2. So these two become another building block B4. Now L2 can be changed to B2 if you want. Then the following statement is the leader, because I equal to 1 is following a conditional go to statement. After that L3 is another leader, so B5 contains only I equal to 1.
The first line of a program is a leader.
Yes, first line of a program is a leader. Yes. And as I said, the target of a conditional or unconditional go to is a leader, and anything which follows a conditional or unconditional go to is also a leader. So that way we have come up to B5, and then as I said, L3 is a leader. So from L3 up to the last statement is in a separate building block. And again, it is giving as B6 as the target, but you could keep the target level L3 as well. So you can see a sequence of 3 address statements on the left hand side is now translated into a sequence of 3 address statements partitioned into basic building blocks. And you can see for each of these basic building blocks, there is a single entry and a single exit. You don't have any exit or entry in the middle. Okay. So it simplifies the
Sir,
step. Yes.
Sir, how you are partitioning from B5, B4, B5, B6?
You are breaking.
Sir, how you are partitioning?
You are breaking.
Sir?
Yes.
Sir, how you are partitioning B4, B5, B6?
As I said, you identify the leaders, and starting from a leader to the next leader, before the next leader is a basic building block. So I equal to 0 is a leader, j equal to 0 is also a leader. So I equal to 0 is the only statement in B1. Similarly, j equal to 0 is a leader, and the following statement is also a leader. So j is assigned the value 0 is in B2. But then, starting from third statement, there are a sequence of statements which are not leaders. Only after the conditional statement, if j smaller than 10, the following statement is a leader. So starting from T1 equal to 10 star I till if j smaller than 10 is basically the building block B3. That's how we have partitioned it. And this is the algorithm. First, you calculate the leaders in step 1. There are 3 rules, as I said. The first statement, the target of a branch statement or jump statement, and the statement which follows a branch or jump statement, they are all leaders. And then in step 2, once you have identified the leader in step 1, for each leader, you include in the basic block corresponding to that leader all the statements which follow the leader till the next leader.
If sir, a basic block can contain 2 leaders.
No, a basic block can contain only 1 leader. If there are 2 leaders, you have to partition them in 2 separate building blocks, basic building blocks. Okay, basic blocks. All right.
Like sir, before you have B3, before there is 2 leaders, so you have partition like this.
Not only that, B1, B2, there are single statement blocks, but they cannot be put together because they are all leaders. I equal to 0 is a leader also because it is the first statement, and j is equal to 0 is also a leader because it is the target of some statement.
Sir, but according to this leader, the algorithm, sir, the first statement is leader. So here j equal to 0 is not first statement. So
no, as I said, it is because of rule 2. Rule 2 says the target of any branch is a leader. So you can see the statement if j smaller than 10, sorry, if I smaller than 10, go to L2.
Okay.
So L2 is a leader. L2 is nothing but j equal to 0. Okay.
Okay, go to line number 2. Okay, sir.
Not line number 2, label L2. Okay.
Level L2.
Label L2. Now, this guy is confused a little bit because he, instead of L2, he is omitting L2 and just referring the L2 as B2. That you can do, or you could keep L2 here. Okay, no problem.
Sir, here number of edges can be asked.
Number of edges, yes. Number of edges is basically the edges which connect the building blocks, and that together forms the control flow graph. So this is also a graph where the nodes of the graph are the basic blocks, and the edges are basically the ones which are connecting them. Okay.
In your gate question, I saw that it is given that find the number of edges of these type of things.
Yes, the number of edges you can easily find from B1 to B2, from B2 to B3, from B3 to B4, and then is one from B3 to B3 to itself. Okay, so that is another edge. There is another after B4 to B2, so that is another edge. So you can easily construct the graph, and then you can find out how many edges are there. Like for example, for this corresponding thing, you can do this. Like, say you can say this is B1, and this is B2, and this is B3. Okay, and then from B3, so this is an edge. So you have to basically compute the edges, and this is from B1 to B2, and then B3. There is a loop here, and then this is B4, and from B4 you go to B2. Okay, and then so here you can see how many edges are there. So this is edge, this is an edge, this is an edge, this is an edge, and this is an edge. So there are 5 edges. So from a graph you can easily compute the number of edges, right? That's how you do it. Okay, you first construct the graph. Graph means each building block is each basic block is a node in the graph, and they are connected by these nodes are connected by the edges, which are basically the control flow, nothing else. Am I clear? Am I clear to know?
Yes, sir, clear.
Okay. The last topic is DAG representation of basic blocks. This is also a favorite question among the examiners. So how do you represent a basic block as a directed acyclic graph? So instead of control flow graph, you can as well represent as a DAG. Now, in order to represent the basic blocks as DAG, there is a reason why we need to do that. Okay, first let us consider an example. So here you can see the example. So here the graph is constructed very intuitively, as you can see. T1 is assigned the value 4 star I. So here the graph is nothing but the children are basically, there are two children. So these are the operands. So 4 and I are operands, and T1 is the T1 is the basically output result, and star is the operator. So operator is kept in middle, as you can see. So for example, if I take this one, if I do this, so the idea is that you create an internal node which consists of the operator. So like a star, and the two children are the two operands. So one is 4 and another is I, and the output is T1. So you assign the label T1 in the internal node. That's what it is. So leaves are labeled by unique identifiers, either variable names or constants. The leaves represent initial value names, and we subscript them with 0 to avoid confusion with labels denoting correct values of names. So here instead of I should use I0 because that is the initial value. But then I can be updated, so it will contain, I will contain the more updated values. I0 is the initial value. Now, T2 is A T1. So T1 is here, and as you can see here, T1 right here, and this T1 is basically operated by the bracket operator to produce T2. So it has T1 right here, and this is the internal node corresponding to the bracket operator. Bracket operator means it's an array operator, and the other end is A, and here you assign the value T2. So this is how you create the DAG. Then T3 is 4 star I. So 4 star I is T3. So this is the same node, 4 and I star. So side by side T1, you assign the value T3. So this is why DAGs are so powerful, because they can immediately identify if there is any common sub-expression or not. Like for example, here, this expression and this expression are the same expression. These are called common sub-expressions, which appear very frequently in code generation or intermediate code generation steps, because these are mechanical steps. So if you can...
cycle can happen in DAG?
Cycle cannot happen because it is an acyclic graph. Cycle will never happen. So these are, as you can see, common sub-expressions, which are two different statements in the generated intermediate code, but you can identify these and you can do the optimization. So as you can see readily, you can optimize using DAGs. That is one of the classic examples of its usage. Then the fourth statement is T4, B T3. So T3 is here. And this is B. So it will give you T4 like this. Then T5 is T2 and T4 star. So this is T2 and this is T4. So you can multiply them and you will get T5. Then T6 is prod plus T5. So you can do this plus prod 0. And this will be your T6. Like this, you create the DAG. So we come back to the DAG construction process. So leaves are labeled by unique identifiers, either variables or constants, and there is a subscript given. Interior nodes are labeled by operator. As I said, nodes are also optionally given a sequence of identifiers for labels. Okay, so whenever a temporary value is created, it is actually labeled in the internal node. The intention is that internal nodes represent computed values, and the identifiers labeling a node are deemed to have that value. Okay, so we have already seen the construction process of DAG, and this is the DAG corresponding to the TSC on the northwest corner. What is the application? We automatically detect common sub-expression. I have just told you. We can determine which identifiers have their values used in the block. That means they have to be the they have to be the children of sub-internal nodes. These are the values which are used. So those which are not used as leaves or as children of some internal node, that means they are not used in the block. So you can understand the use information from the DAG, and we can determine which statements compute values that could be used outside the block. That means all the internal nodes which are labeled with some values, that means they will be used outside the DAG. So these three tasks can be accomplished with DAGs. As we will see, this common sub-expression elimination is a very important step in code optimization, which we will be studying in the afternoon class starting from 12:40. Okay, so use information. Next use information as can also be determined, and the ones which are live after this block is also available from the representation of DAGs. This is where I stop the class. Now there are a bunch of statements in B5 starting from 14 up to starting from 14 up to 22, then 23 is a leader. So let us write this block. So 14 is E6 is assigned the value 4 star I, then 15 is X is assigned the value A T6, then 16 is assigned the value T7 equal to 7 is assigned the value 4 star I, then 17 is assigned the value T8 4 star J, 19 is A T7 is assigned the value T9, 20 is T10 is assigned the value 4 star J, 21 is assigned the value A T10 is assigned the value X, and 22 is go to 5. So this was the sequence of code. And this is B4. Sorry, this is B5. So 13 branches, one goes to 23 and another goes to B4. Sorry, B5. So this is B5. So one branch comes here, another branch will go to B6 as we'll see. Okay, and this is going to go to B6, and B6 consists of 23, which is a leader because it follows 22, which is an unconditional go to statement. Then 23, 24, 25, 26, 27, 28, 29, 30, all of these are part of the same building block, same basic building block, which is B6. So let us write that here. So we have 23, which is T11 is assigned the value 4 star I. Then 24 is X is assigned the value A. T11. Then 25, T12 is assigned the value 4 star I. 26, T13 is assigned the value 4 star N. 27, T14 is assigned the value A T13. 28, A T12 is assigned the value T14. 29, T15 is assigned the value 4 star N. And to 30, A T15 is assigned the value X. Okay, so this is how B6 looks like. And this is B6. So this is the control flow graph. And of course, there are some more loops actually from 8. It will go to 5. So like this, there is a statement here. And 12, it will loop here. So it is a self loop here. from 8 to 5, so it will be also a self loop. Sorry, this is not the one. Yeah, so it should be like this. 8 to 5, so it is within B2. Then 12 to 9, so this is within here. And then from 13, one will go to 14 and another will go to 23. So there are two. From 22, one will go to B2. So from here, there will be an entry here, right here. That's 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 the one. There is nothing else. Yes. Okay. So this is how the graph looks like. Control flow graph looks like. Now the question is, what are the types of uh, optimization we can do? The first thing we talked about is common subexpression elimination. So common subexpression elimination is something we can do first, as you can see in on B5. So let us try that on B5 itself. So let's take B5 and duplicate it and get it to some other place. This is B5, as you can see. So here there are quite a few statements which are repetition of the same expression. Like you can see 14 and 16. They are basically the same sub expression, common sub expression, 4 star I. Similarly, 17 and 20, they are the same sub expression. You can see T8 is 4 star J, T8 is assigned the 4 star J, and T10 is assigned the value 4 star J. So they are both using the same sub expression. That's this. So this is known as common sub expression elimination. So we can eliminate it. So common sub expression elimination. Now, what you can do is you can remove these sub expressions. The first one you can keep. You can remove the other ones. So for example, you can see that we can keep T6 for 4 star I. So let's keep this. 15 is not a problem. Then 16 we can eliminate. Okay, so 16 we can definitely eliminate. Then 17 is 4 star J, another new expression. So we can keep that. Okay, now I'll come to 19 a little later. Just wait a little bit. 19 is an interesting story. I'll come to that. Okay, then 20 is a repetition of 17. So because there is the same sub expression 4 star J. So we can eliminate 20 as well. And then 21 dependent on 20. So let's put another star mark here. And then go to 5. So here you can see we have reduced from 9 statement to 6 statements. 8 statements to 6 statements. Okay. So statement number 17, statement number 14 and 17 stayed, but statement number 16 and statement number 20 are gone. Okay. So this is an example of common subexpression elimination. But then common subexpression elimination has a propagating effect. What is that propagating effect? You can see that there are statements which dependent on the later subexpression assignments. Like for example, 19 dependent on 16, because 19 is using T7 and T7 is computed at 16. But then we removed T7. Okay. So what exactly we are trying to do? We are removing T7 and instead we are always using T6, right? Because
So এই স্টেপটা বুঝতে পারলাম না, রিমুভিং T7 এর মানে আগের স্টেটমেন্ট।
হ্যাঁ, see 16 is removed, right? Because 16 and 14 they both compute the same sub-expression, right? 4 star I, right?
Yes, sir.
So according to our algorithm, we'll keep the first one, we'll eliminate the other ones. So here 16 is removed, right?
Yes, sir.
As you can see on the right hand side, as you can see, statement number 16 is removed. Okay. And
Yes,
similarly,
sir.
statement number 20 is removed. Okay.
Yes, sir.
Now, what will happen to 19, which depends on 16? As you can see, 19
সে
has
14 সে কানেক্ট করে দেবো,
কি করবে?
14 থেকে কানেক্ট করে দেবো 19 কে।
Right. So that means what you need to do, you need to eliminate common sub-expression, and then what you need to do is propagate the original copy. Okay. This is what
স্যার
is
এই
known.
জিনিসটা আপনার অটোমাটার এপসাইলন এলিমিনেশনের মতো না অনেকটা?
Don't know. I have never given any thought. Could be. I think it is a little different. It's known as flow optimization, but could be. I mean, of course, ideas come from one domain to another. Okay. Now, this technique, copy propagation, what it does is, you can see T7 was nothing but a copy of what T6 was doing. So instead of, when you eliminated T7, you generally need to propagate the copy, which is T6. So that means wherever T7 is used, you have to change that to T6, like right here. Okay. So that means we can remove the star from 19. Again, for statement number 21, T10 dependent on 20, but there is no 20 anymore. 20 was computing T10, and T10 is actually being generated at statement number 17. So that copy T8 can be propagated to 21. So we can say like this, and then we can remove the star here as well. Okay, so you can see that we are not only eliminating common sub-expressions, but in the process, we are doing something called copy propagation. That you have to do in most cases, because some places, the statement you are eliminating, the sub-expression you are eliminating may be used further down the road. So you have to propagate the original one, that is the copy. Okay. All right. So we have seen that we could substantially improve the code from the original one to the optimized one using these two techniques. And now we can do the same for the whole graph. Okay, so let us do that. So we have it here. So here what we'll do is, we'll make it a little larger now. So I is assigned the value m minus 1, j is assigned the value n, t1 is assigned the value 4 star n, and v is assigned the value 81. We cannot do much here. But let's see, in B2, I is assigned the value I plus 1, T2 is 4 star I, T3 is a T2, and then something. Okay. Here, so nothing doing there. In B3, you can see J is assigned the value J star, J minus 1, T4 is 4 star J, T5 is A4, and blah, blah, blah. So 9 through 12, we cannot do much. In 13 also, we cannot do much. But as we have seen, in 14, we can definitely make some improvements. And here, instead of T6, what we can do is, where are we generating, where is the place we are generating 4 star I first? In statement number 6, right here. Right here. This is 4 star I. Okay. So this statement can be used for common subexpression elimination. And that means what? That means you can propagate T2 from B2 to B4, right? At statement number 16. Okay. So what we can do here is we can eliminate this statement number 14. But you can see, so instead of that, we can say use P2 instead of P6. Right? So now in 15, we can write this. Instead of T6, use T2. Similarly, 16 can be eliminated, and we can do the same thing. Use T2 instead of T7. We can say use T2 instead T7 because they compute the same sub-expression. Okay. For T8, 4 star J, we can see that statement number 10 is computing the same thing right here, which is 4 star J. So T4 can be used in place of 4 star J. So at statement number 18, sorry, statement number 17, we can say use T4 instead of T8. Fine. Now 19, you can see statement number 19 is using T7. We can use T2 instead of T7. At statement number 20, again we have 4 star J. So we can use T4 instead of T10. Instead of T10. Now statement number 21 is using T10, so we can use T4. And then 22 go to 5. Let us look at block B6. So block B6, T11 is computing 4 star I. So use T2 instead of T11. 24 is using T11, so you can use T2. T12 is computing 4 star I, so again use T2 instead of T12, not T12. T13 is 4 star N. 4 star N is computed at statement number 3, which is T1. So you can say at statement number 26, use T1, not T13. Now T14 is using T13 in statement number 27. So we can use T1. In statement number 28, A12 is assigned the value T14. Statement number 29, T15 is 4 star 9. Now 4 star n. So 4 star n is computed at statement number 3 and it is T1. So use T1, not T5, T15, sorry. Use T1, not T15. And 30, we can say AT1 is assigned the value X. Okay. So we are done with first pass of the common sub-expression elimination, which is eliminating T1, eliminating 4 star I, 4 star J, and 4 star N. Okay, we have done that. All right. Now, what we can do is you can see that statements 14, 16, these things are already eliminated. So let's eliminate these statements. Because they are nothing, they are eliminated anyway. As soon as the expressions are eliminated, here also you'll be having lots of eliminations. And we don't have a problem. Okay. This is how our optimized code looks like till now. Now, is there any further scope of improvement? Let's see. Now, you can see that AT4 okay. Okay, we can see that statement number 7 is computing, this guy is computing AT2 and it is assigning that to T3. Okay, now you can see that this guy, statement number 15, is doing the same thing. Okay, X is assigned the value AT2. Now you can see that T3 is assigned the value AT2 already, so it has a copy of AT2. So why not propagate the copy T3 instead of AT2 to statement number 15? So here you can say X is assigned the value T3. Similarly, at statement number 24, you can say X is assigned the value T3. Here you are propagating something which is of lower computation cost because T3 is a temporary which is assigned an element from the array. As accessing an array element is much more time consuming compared to accessing a temporary. Okay, so you can easily use T3 instead of a T2 in statement number 15 and statement number 24. Okay, because you have the copy at T3. All right. Now what? Now let's see. Okay. I think I mistakenly deleted statement number 18 as well. Statement number 18 should be here actually. Statement number 18 is T9 is assigned the value. I somehow missed it. A T4. Okay. Oh, it was a T8, and T8 was actually a copy of T4. So yes. So this was the thing. 18 I missed. Sorry. Okay. Somehow I deleted 18. Okay. Okay, I'll come to T9 a little later. Okay, let us complete the other things. As you can see, in statement number 28, a T12 is assigned the value T14. Now T12, as you know, is 4 star I, and 4 star I is basically computed at T2. So instead of T12, we can write a T2. Okay, all right. So we cannot do any more in B6. B6 is fully optimized, and B1 through B4 nothing doing. For B5, statement number 18, let us look at statement number 18 again. So statement number 18 was,
So এটা কি রাইট রিকার্সিভ হবে জিনিসটা?
না রাইট রিকার্সিভ না, এটা হবে মাল্টিপল পাস। ইউ হ্যাভ টু ডু মাল্টিপল পাস to complete the optimization process as much as possible. Okay, so in your exam or in your assignments, you will be always specified the number of passes you have to try, because it can go for a long period of time. Okay, because once you do this, then it will be having a propagating effect on the copy propagation, and that will cause further optimization. So it can go on for quite a few passes. That's why optimization takes a long time. And when you did that GCC thing, you had to explicitly use optimization levels to implement more and more optimization. That is basically you are increasing the number of passes and increasing the number of techniques. Okay, now let us look into 15 through 22 in B5. So in B5, originally 18 was T9 is assigned the value AT8. So let us start from there. So this was the original one. T9 T9 was assigned the value AT8. Okay. Now T8 was 4 star J. 4 star J is basically T4. So we made it as T9 is assigned the value AT4. Okay. Now you can see that statement number 11 right here, T5 is assigned the value AT4. Okay. So 11 is a common sub-expression with statement number 18. Okay. So you can eliminate statement number 18. Okay. So eliminate 18 and instead of T9, use 84, which is given to 11, which is a copy of 84. So you can write T5. And that's what is done here. Okay. So this is the final optimized version after common sub-expression elimination and copy propagation of the given code. So from 30 statements, as you can see, we are down to 12, 13, and then we have 8. So 21 statements right now. Because of these two techniques we have used. First, we eliminated 4 star I, 4 star N, 4 star J as sub-expressions, common sub-expressions. Then we further did the optimization using copy propagation of T4, T5, etc. And then that had triggering effect on further common sub-expressions, like we have seen AT4 was replicated in many places, and AT1 and AT2, etc. So those things could also be changed. Okay. So now we have this kind of thing after 2 rounds of optimization. Okay. And this is already mentioned, the copy propagation technique.
Sir, how many rounds of optimization required?
See, it is difficult to say. Okay. You will see in GCC there is minus capital O1, minus capital O2, minus capital O3. So it keeps on doing. Okay. If you give minus O3, it will take much more time than minus O1 and minus O2. We have tested it. You might have tested it as well in software tools lab. So we don't know, frankly speaking. You have to look into the manuals. Okay. But in exams, 2 to 3 round is sufficient. Okay. Not more than that. Okay. Now the next one is date code elimination. So you have seen 2 techniques, copy propagation and common sub-expression elimination. They go hand in hand. Similarly, another thing which goes hand in hand is date code elimination. A variable is live at a point in a program if its value can be subsequently used. Otherwise, it is dead. It is related to the idea of dead code or useless code. Statements that compute values which are dead means they never get used.
মানে স্যার ধরুন আমি একটা ভ্যারিয়েবল এ ডিক্লেয়ার করলাম এবার এটা আমি কখনো ইউজ করলাম না, তো সেটা ডেড কোড বলতে পারি?
That is dead code. Kintu remember one thing, you as a programmer will never do that. But as you have seen, these intermediate code generation and code generation steps are pretty mechanical. So they can create this kind of dead code. And if you use further optimization, they can even produce more dead code, as you'll see shortly. Okay. Like for example, an example is given here, if debug do something. Now, if you remember, in your software tools class, you had GCC minus D debug. That was given as a command line option. If you don't give debug option, then debug will be turning to 0, and all the code which goes with if debug is useless. because they will not be reached. This is the compile time option. That happens because you don't want to include the debug code in your production code, right? You remember all those things from software tools, production release and debug release and stuff like that. Debug release means your code will be there. Like -G option you had for GCC, that actually includes those debug code. Otherwise, it won't be there. Okay. So another interesting technique which can cause dead code is known as constant folding. Deducing at compile time that the value of an expression is a constant and using the constant instead is known as constant folding. We'll see it can cause a lot of, it can give rise to a lot of optimization opportunities. Now, copy propagation giving rise to dead code is given here. Okay, right here, which we have seen in statement number, which we have seen in block B5. What is that? So you can see that T3, as you can see, T3 is coming to X, okay, in statement number 15. And then X is used in statement number 21. So T3 is a copy which has propagated to 15, and then that copy is propagated to 21. So can we do this? Instead of X, we propagated T3, we propagate T3 to 21. And now you see the code. 15, X is assigned the value T3, 19, A2 is assigned the value T5, 21, T4 is assigned the value T3, 22 go to 5. Now what about 15? What is it doing? It's not doing anything because it is computing a value which is dead code because X is never used. So we might eliminate this as well. As you can see, copy propagation, because you propagated T3, which is a copy of X, to 21, that's what caused this interesting improvement opportunity. Similarly, you can do the same for statement 24 and 30. Here, instead of X, you can put T3, and then 23 is a dead, 24 is a dead code. You can see B6 and B5 are further optimized. Okay. Okay. So up to this much, we are talking about individual block level optimization or inter-block optimization. Now, there is another interesting type of optimization. In fact, this is the most important one, which is known as the loop optimization. Because most of the time programs are concentrated in a few loops. And if you have inner loops, there will be even more. So if you can improve any of the loops.
So this is done by the programmer itself.
No. These are all done by the compiler. The compiler has a phase, has multiple phases actually. It works in multiple phases, but it can try the optimization. Okay. So this is loop optimization. This occurs not by the programmer, this occurs by the intermediate code generator. This is done by the intermediate code generator, especially the inner loops. Okay. So three techniques. One is known as code motion, which moves code outside a loop. So if you do something inside a loop and if you can remove it into the outside, that is a huge improvement. Like if you have a statement inside a loop which is executed 10 times, if you can move the code outside, then it is executed only once. So you have a great improvement. Then induction variable elimination, we'll see what is meant by that. And then reduction in strength, which replaces an expensive operation by a cheaper one. Like for example, you can use addition instead of multiplication. Addition is much faster compared to multiplication. So these are the three techniques you can use for loop optimization. You might have seen a little bit of that during your GCOV days. Okay. Here is an example. Expressions which are not evaluated in the code must be moved out of the loop. This is a big problem sometimes you as a programmer also do. You keep constants, you keep constant assignments. These all are inside loops. Why do you do that? Like, for example, you see something which we very often do. Why I is smaller than or equal to limit minus 2, and then we go into the loop where we don't change the value of limit. So what you are doing essentially is, you are, say, suppose you are executing the loop 100 times. 100 times you are computing the value limit minus 2, and there is no need for that. Instead of that, you could compute it only once outside the loop and assign it to a temporary variable and use that instead. That would greatly improve your code. So this is an example of code motion. Next comes the interesting idea of induction variable and how we can eliminate it. Now, this is an interesting thing. Let us look into the example we are going through.
Sir, for example, in a program I have given, sir, I am using nested loop, but if it is not required, compiler will automatically cut off.
Absolutely, absolutely. Here is an example you can see, interesting one. Like, for example, you can see that let us look into the example of T4 and J, statement number 10, right here. Statement number 10, T4 and J. See, T4 and J are not independent. J and T4 move in a lockstep manner. So if J increases, T4 increases by 4. We agree, right? But you can see that T4 is evaluated inside a loop, right? So B3 has a loop, and there is a loop from B5 to B2 which goes via B3. Similarly for T2 and I, they also move in a lockstep manner, and this expression is calculated in a loop. So this kind of scenario, note that the values of J and T4 remain in lockstep. Every time the value of J decreases by 1, that of T4 decreases by 4, because T4 is nothing but 4 star J. Such identifiers are known as induction variables. So T4 is an induction variable, because if we know the value of J, we can directly infer the value of T4, and vice versa. When there are 2 or more induction variables in a loop, it may be possible to get rid of all but one. So you can keep just only one by the process of induction variable elimination. And that greatly reduces the running time of a loop. How? So what we do here is, we initialize T4 in B2 instead of B3. You can see T4 is at statement number 10, which is at B3. So what we do here is, we put another statement after 8, and let's call it 8A, where we say T4 is given the value, that we can do it right here in block B1, yes, which is the initial block. So here we can say at statement 4A that T4 is assigned the value, say, 4 star n, because J is n, so T4 has to be 4 times that, which is 4 star n, or 4 star J, not a problem, 4 star J. And then here, instead of computing T4 as 4 star J, what you can do is T4 is
T1.
T4 minus 4, because every time j is decremented by 1, as you can see. Okay, so T4 is there, no doubt, but you are not computing 4 star j anymore. And you know that computing T4 minus 4 and 4 star j, which one is easier? Of course, the subtraction is a easier one. So you can use induction variable along with reduction in strength to do further optimization of loops. And as you can see here, in B3, uh, instead of computing T4 equal to 4 star j, you are computing T4 equal to T4 minus 4. That's it. So this is,
Sir, this line may you repeat once again, sir.
yeah.
Foster J, how I am replacing?
So what I am doing is, you know that T4 is always going to be 4 of j, 4 times j, right? And in
Yes, sir.
loop, j is always decremented by 1, right?
Yes, sir.
So instead of computing 4 star j every time, what you can do is you can replace T4 equal to 4 star j by T4 equal to T4 minus 4. Can you
Yes,
do
sir.
that? Yeah.
Yes, sir. Minus 1.
T4 minus 4, because j is decremented by 1, so T4 should be decremented by 4.
Yes, sir.
So this is what is known as identifying induction variable and replacing it by a reduced strength operator.
Yes, sir.
Subtraction is much reduced in strength, means it takes much less time to execute compared to the multiplication. So that's a huge saving, because this saving is not prominent if you run it only once. But since we are talking about loop optimizations, if you run it 100 times, that would be a huge improvement. Okay, but
Okay, sir.
you have to keep an assumption that j and T4 should be induction, means they should be moving in lockstep manner. Now, if j got incremented somehow in a different manner in other part of the code, then it won't work. Okay. All right.
So
So
what do you understand? Sir, what do we understand by that inductive step?
inductive step means whenever j changes, T4 changes by the same amount. Means if it is changing by 1 in the loop, T4 should always change by 4. Now it
Okay,
should
sir.
not happen that j changes once, you increment j by 1 and then you decrement it by 1, and then you think that T4 will be incrementing by 4 and decrementing by 4. That might not happen. So in that case, you cannot do anything. It's not induction variable anymore. That's what it is. Only if they move in a lockstep manner, as I said, if this guy changes by some amount, the other guy changes by an exactly similar amount, then they are induction. Okay. Here they always change. Whenever j changes, T4 changes by 4. That's it. That's why they are induction. You can
Okay, sir.
identify such variables. Okay. As I said, T1 also can give rise to some variables. Okay. Now they have given. So okay, let's see what are the other induction variables we can find here.
So
So
what type of question can we get from loop optimization?
I have already given you an exercise as assignment, which you should submit. There, I have given you an example. So all those techniques which you have to apply in multiple passes. Okay. So when you are done with common sub expression and copy propagation and date code elimination, then should you go for loop optimization. Like for example, here you can see that statement number 10 is now very easy to execute. Now another opportunity is there as well. You can see statement number 5 is I equal to I plus 1. Okay. So here also you can say T2 is T2 plus 4, right?
Yes, sir. T2 is T2 plus 4. It is easy.
Which is easy, right? So that is what they are doing here. T2 equals to T2 plus 4. Okay, another important thing is that if you do such things, you don't need to initialize I uh, here. I mean, you can keep it here, but instead you can do this for B T2 is 4 star I. Let's see if we need I at all. Okay, you can see that I is every time incremented by 1, but I is never really used. Okay, I is only used in statement number 13. Okay, so I is greater than j. Now, instead of, so here the expression is very interesting. I is greater than equal to j. So that means 4 star I is greater than equal to 4 star j, right? Right? 4 star I is what? 4 star I is T2 and 4 star j is T4. So instead of I greater than or equal to j, you might as well write T2 greater than T4. And that means what? That means you don't need I. Statement number 5 is not needed. And then statement number 9 is not needed. So you are removing 2 statements in loops. That's a huge improvement. So you can see that eliminating induction variables can actually reduce the number of statements per loop, which is a great improvement, as you can see right here. So in B2 and B3, you can see you have reduced the number of statements by 33%, 25%, which is great. So instead of 4, you are executing only 3, and these loops may be executing hundreds of times. So that's a huge improvement. Okay, I don't think there is any other improvement opportunity here. So we can go to the next one. Okay, so we have already seen strength reduction. So strength reduction means costly operators should be replaced by cheaper operators. Like you can, instead of x to the power 2, you can say x star 4 by x left shift 2, etc.
Sir, in one book I saw that it is written that, for example, you are printing something 5 times using loop, then you can simply print the statement 5 times.
That is much better, right? Yeah, I think you are right. True, true, it's true. In fact, that is what is known as loop unfolding or loop unrolling. It's a very useful technique for architectural optimizations, which is needed for high performance compilers. This used to be taught in architecture and in compiler as well. Nowadays, somehow it's gone. Okay, but that creates some other problems. Uh, Unfortunately, I don't have the time to discuss all these things. Anyway, then comes algebraic transformation. So you should eliminate addition and subtraction with 0. It has no meaning. You should eliminate multiplication division by 1. You should eliminate multiplication by 0, because you can easily replace that with 0. There is no point in multiplying with 0, right? So you can as well assign 0 to x, and there is a statement called CLRx or XOR x comma x, which does the same thing, which are very cheap operations. Now we come to last few pages of our discussion, which is peephole optimization. Peephole optimization is an interesting thing. So just wait for a few minutes. Okay, I'm back. Okay, so peephole optimization for a change is specific to the code generation phase. You cannot do that. Probably you can do for other phases as well, but it really has a meaning for code generation phase. Now, I always like to uh, compare it with our local information. Like, for example, um, if you have a local expert, you may go to him and ask for, say, compiler help, and he will do that. It's not that he's the most efficient expert in the world or knowledgeable expert in the world, but he's good enough for you. So you ask him some question and he will give you a good answer. Then you go to some other persons who are even more expert than him, and you get more information. Okay. So when you go for code generation, it is very difficult to do at a very global level. So what we do is we try to do the optimization at a very local level. And that means instead of looking beyond a few lines of code, we focus on a few lines of code. So as if you are sliding a peephole on your code. So suppose the code is, say, 100,000 lines of code. So you just highlight 5 lines. It's like a highlighter. You are sliding on your code. And whatever is highlighted, you just see whether there is any opportunity to improvement. That is what is known as peephole optimization. The term peephole exactly means that. Consider a sliding window of instructions and optimize it. So that means you have to do repeated passes, because it might happen that you look at 3 lines of code and you do the improvement, you do further 3 lines of code, and that way you do improvement there also. But then if you increase the size to 4, it might throw in more opportunity. Redundant instruction elimination, we'll see. So these are some interesting techniques which generally happen only in the code generation phase because of the mechanical nature of the code generation algorithm. Redundant instruction elimination is a new one. Dead code elimination we have already seen. Control flow optimization, algebraic simplification we have already seen, and use of machine idioms. So these are the 5 types of peephole optimization, which is very common among the optimizing compiler writers. Okay. So what is redundant instruction elimination? We have already seen an example in the morning today. So you move R0 to A, and then you load from A to R0. This is totally redundant because the value is already in R0. So you might as well remove these 2 statements and keep on using R0. Okay. So this kind of instructions will never be written by any rational person, but as I said, compilers are basically mechanical thing, so they can produce this kind of code. Dead code elimination we have already said. Control flow optimization, jumps over jumps or multiple jumps. What is that? You can see, go to L1 and then it is a go to L2.
Is it nested loop, sir?
Sorry?
This is nested loop, I think.
No, this is not nested loop. This is plain vanilla jump over jump. So from L1, you are jumping. So let us explain this. I think this will be helpful. So there are 2 things. Go to L1, go to L3. Let me write this. That would be even better. So here you can see that so this is a jump right here, and this is a jump right here. This is basically jump over jump. So you are jumping over another jump. Okay. So why don't you do this? Instead of that, what you can do here is Why don't you do this? Go to L2. You don't have to do anything. Okay, this is an example where multiple jumps are avoided. So L1 is coming to L1. Sorry, this statement say call it as say L0. So in L0, what you are doing is you are jumping to L1, and from L1 you are jumping to L2. Instead of that, what you can do is do direct jump here, and that's what is happening here. So you remove unnecessary operations. That L1 is not needed at all. You can scratch these. Not needed. Algebraic simplification we have already talked about. And then the last one, which is use of machine idioms. I have repeatedly told that in past also, not a whole lot of people actually pay attention to that. Like for example, load R0X, add R0, R01, store X R0, push X, push %ESP, go to fun. Instead of that, what you can easily do is INCX. INCX is an operation which does exactly the same thing as
the increment.
first three tests, right? First three statements. But the beauty of INCX is it is highly optimized. This kind of optimization is done at the firmware level or micro instruction level. So this.
Sir, I think it is used in 8085.
True. And there are many such examples, okay, where instead of a more complex and difficult to execute instruction, if you use the right instruction, which that can enhance the performance by a million times, because these instructions are hard coded in your microcode, and so micro architecture based optimization can be enabled. And this is not only done by compilers, but performance engineers also tend to do that very often. So they will help or guide system developers and programmers as well to choose such instructions. And that's why you keep on hearing that you cannot always use high level constructs to produce the most highly optimized code, because that might not always use the most available, most efficient machine idiom. Okay, so sometimes you might have to embed that kind of code in your program. Like for example, in Linux, you will keep on hearing that there is a lot of assembly level code embedded inside the Linux kernel to make it much more efficient, real time, etc. Okay, this is because of this kind of approach, and there are other reasons also, but this kind of approach can actually enable the programmer, which is a human programmer, as well as the machine translator, which is not a human programmer, which is a machine basically, or some kind of a software, to choose the most efficient instruction in terms of time, power, and storage requirement. Okay, and that's about it for this course.